Hi, this is Pablo, and today we're going to continue with the bolts. Okay, remember a few weeks ago, we were starting introduction about bolt groups and fasteners, and after the introduction, we're going to continue with the section 2 or unit 2, which is going to be what you see right now on the screen, which is the stress section and bolt strength. Okay, that this video is going to be a little bit shorter. It's really just a few equations and also talk a little bit of what type of stress are we gonna use when we have to compare our basically the stress that we have due to um, a load or a force and compare that with the strength of the bolt. Okay, so starting with the stress section. Okay, we're gonna talk first about the metric one and then a little bit about the US custom system. The metric we're going to use as a reference the ISO 898-1. Remember from the last video, the ISO 898-1 was the one around the steels, okay? Carbon steels and alloy steels, quench tempered, whatever, okay? So basically, we're going to start with some nomenclature. We're going to start with some few of these parameters, okay, which they're going to be important when we develop the few equations that you can see. It's not like a really complex one. The first one is going to be the diameter, okay. D is going to be the nominal diameter of the bolt, okay. For example, in the metric system for a M5, it's going to be 5 millimeters, of course. M6, 6 millimeters. M20, 20 millimeters. Okay, that is the nominal, okay, a value of diameter of the bolt, okay. Also, in some, okay, this is not completely true. I have to modify that. Not in all of the bolts, okay, but in some then of the regular ones, it's also the diameter of the shank or the unthreaded zone, okay. There's some bolts, like for example, if I'm not wrong, the ISO 4015, I think, the shank or the unthreaded zone is, let's say, narrower than the nominal, okay. This is important to know. So not in all the bolts, but regular ones it is, okay. But either way, we're gonna use D as the nominal diameter of the bolt, okay. 5 millimeters for M5, as you said, 14 for M14, so on, 36 for M36 or whatever, okay. And then we have the H, which is gonna be the height of the thread triangle, okay. Imagine that we just cut uh, imagine that we just cut uh, the thread of the triangle, okay, as a bolt, sorry, like for example here, okay. Let's use a section of the thread. Here we get the H is gonna be this, as you can see here, okay, between the narrowest part and the widest part, okay, that is gonna be the H, in accordance to ISO 68-1. Curiously, to calculate that, we're gonna start talking about the P, okay, which here is, okay. The second most important parameter, sorry, I should have put this thing first, is gonna be the pitch, okay. And the pitch is gonna be the separation of these internal thread triangles, okay, as you can see here, that you can find in any of the ISO dimensional standards like ISO 4014 or the 4017 or whatever you can find, okay. And then you're gonna have two types, okay, of pitch. The what typically they so call, at least here, coarse thread and fine thread, okay. Coarse thread is going to be the regular thread, okay, the normal one, and then you have a fine thread because some bolts they have higher number of or higher pitch for the same nominal diameter, okay. So in this case, for example, we have a small chart that we'll talk in a future video. We have the bolt nominal size, okay. Here is the diameter, and here is the pitch, okay. So for an M3 the pitch is 0,5, M6 1, M8 is 1,25, and so on, okay. So that is going to be the pitch as we said based on this drawing. Okay. Uh, Going back, the height that we were talking before, that height, okay, it can be calculated, of course, based on this angle as a function of the pitch. Okay, and here we have pretty much the value. Okay, as I said, using the 60-degree geometrically. Here you can find it. It's pretty much the same thing. So h is gonna be that one, 0,866,025 times the pitch. Okay, and then we're gonna have the other ones. D1, which is the basic diameter. Okay, in accordance with the ISO 724. That is going to be D1 here, exactly. Then we get, these are really, it's Roymec, of course. We're gonna have this is the equation, of course, is the nominal diameter minus 1,25 times the height. Then D2, which is gonna be basic pitch, D2 here, perfect. That is gonna be D minus 0,75 H, which we can put both in function of the pitch. And then D3 is gonna be that one. And that one is gonna be D1 minus the height divided by 6, okay? So basically we have all these diameters, specific ones based on the pitch at the end and the nominal diameter, okay? And those two things we can find in any of the standards that we were talking before, okay? In any of those dimensional standards that we have here, the ISO 4014, 15, 16, 17, 8765, all these ones, also for the nuts, okay? These ones, they're gonna tell you basically something very similar to this. You're gonna have the bolt size, sorry, which is the nominal diameter, and then they're gonna tell you the pitch. Okay, each one of these ones is gonna have the pitch. The only exception is going to be the ones such as the fine thread. Let me go find it. Threaded. No, well, fine thread. For example, this ISO, which we're gonna have in two type of tolerance. This ISO 8765 we're talking a little bit is a regular hexagon head bolt with a fine thread. Okay, on fine thread is gonna just be a little bit different because, for example, for M10 you can use pitch 1 or 1,25, while in coarse is gonna be 1,5. So the pitch is gonna be smaller. Sorry, I think before I said it was a higher number. I'm wrong. It is smaller. And that means that it's going to have more triangles, more threads per length of the bolt, okay? And that is going to increase, as we will see later, the surface, okay? So as we said, everything is based on the pitch and the nominal diameter, okay? So now we're going to come with the only two really equations that we want to see here, okay? Which is in accordance of the ISO standard, okay, we are gonna have basically two formulas, okay, which are gonna calculate the section, okay, that we're gonna have in the bolt, okay. One is gonna be for the threaded zone, then it's gonna be for the unthreaded zone, okay, or the zone. What is the difference? Well, the unthreaded zone is gonna be basically the, of course, because basically it's a cylinder, the area, or the section is gonna be a circumference. The area is gonna be pi times square d divided by 4. Okay, being the nominal diameter, which is the diameter of the shank. Okay, if the shank has, for example, for the one that is said, I think the 4015, which is a little bit narrower, then it's gonna be that diameter. Okay, but for this formula for the unthreaded zone is not that important, at least for me and for my calculations. Because why? Because a bolt is designed, okay, to fail first in the threaded area or zone. Okay, it is designed for that. So it is designed that it breaks because When you have a bolt like this, for example, and you have a nut here, and the nut probably is going to cover, as we can see here, some of the threads. Not all of the threads are going to be loaded in the same with the same force. Okay, the distribution is not going to be equal. Okay, the first one is going to be loaded higher than the second one, this one more than the third one, and so on. If for some reason one of them you break, then the second one is going to be able to now increase the I mean, it's going to be loaded higher, okay, but it could resist this extra force. So in that way, instead of breaking the whole thing, it would only basically break one of the threads. Okay, that is kind of like a security safety system that exists to prevent the nut for like losing, okay, losing the nut and then have a possible catastrophic failure. Okay, however, based on that, I'm not 100% sure, but I thought based on the Shingley's mechanical design book, uh, statistically, not always it breaks in the thread. Okay, I think it was 65% of the times it breaks in the thread. Then you have another 35% that breaks or in the head or in the shank or other areas. Okay, I guess based on manufacturing process or other reasons. Okay, that problematic. Well, you can pretty much cover with the safety factor or the load factor, and you can still be safe. Okay. Um, so that's the reason why, because it's designed to break on the thread. Basically, the weakest part of the bolt is gonna be the thread. So the area that we're gonna calculate for all the calculations is gonna pretty much be this one. Okay, the AS, which I use as a stress area. There are going to be some cases, for example, in a double sear, that maybe one of the plane that is going to be in, I mean, the sear plane, it may cross the shank. Okay, it may be the sear one being here. Then you should technically you should use that second equation, but in reality, at least for me, to make everything more homogeneous, I always use this one, so I don't have to use, depending on the case, different equations. That makes my charts a little easier. I know it's a little bit conservative in some specific cases, but then you don't have to go in each time and then check exactly where the failure plane is gonna, I mean, the shear plane is gonna be intersecting the bolt. You consider that the weakest part is gonna be that, so all the bolt is gonna be basically the thread. Okay, so that equation, which is very similar, you only calculate basically between the D2 and D3. You get an average of those, which is this D2 plus D3 divided by 2. We see the D2 and D3 is going to be there. So it's going to calculate the average of those, and you calculate the area considering that that is going to be the diameter. Okay, and this is based on the ISO 89A-1, okay, which is the pretty much the most important standard for bolts, at least in the metric world. Okay, so as I said, you have all equations here. I will upload this document into my website, and then you're gonna be able, if you want, to check these things. If not, just go into ISO, the standard, and you're gonna find the same equations. Or for example, here, this website, Roymec, as many people know, is as good or even better than my things. So you can go there. They're gonna have all these small equations and then the final one. Okay, so we finished talking about the metric stress section. It is important to say why we're gonna calculate that, because a stress section is gonna be the ratio in a way between the force and the stress. Okay, so we're going to calculate the difference between force and stress, okay, that is applied in a bolt, or the resistance, okay, the strength. Then we're going to use this stress area, okay, which is going to be, as I said, the ratio between these two ones. Okay, and now we're going to talk a little bit about the US custom and called Imperial, okay, based on ISIC design criteria, which you can find, I think I would check this one, which is pretty good. Okay, this is one of the best documents I have for bolts. Okay, I recommend to check it. It's for US. Okay, so all the standard are going to be US, which we check a little bit, which it doesn't matter. This one, okay, for the American Institute of Steel Construction is one of the best, at least for the US standards. And they have a, I forgot the page, but when you go, you can find this equation, which is going to be basically the same thing, okay? I just resumed that a little bit uh, in only one equation to make it a little bit faster. And the same thing, you have the D, nominal diameter, you get the N, okay? And then of course, which is the number of threads per inch. Again, I'm going to explain this a little bit. And then you get the area of the stress, okay? The same thing with the sank is the same as before. This one is a little bit different for a couple things. One, these coefficients, okay, which are like a subproduct of all these type of equations, but in the imperial system, and the N, okay? In the US, instead of using the pitch, typically when you're going to talk about a bolt, for example, you're going to select the half inch 13 UNC. That 13 or 1/4 20 or 1/4 28 or 5/16 18 or 3/8 16, that second number, okay, is going to be, instead of the pitch, they use number of threads per inch, okay, which is one divided by the other one. So you count in 1 inch, you can measure in the bolt, you can count as many, all the threads that you get, and that is going to be this number, okay, which is one divided by the pitch, okay. So as I said, in US, you're going to use that rather than the pitch, which is very easy when you get for example, list of US type of threads, okay, I'm talking about regular bolts. You're gonna get the typical list, which no, we don't find here. For example, those are the typical numbers, okay, fractioning in inches, of course, 3/8 of an inch, and then you're gonna get the coarse, which is gonna be 16, or the fine, that is gonna be 24. So this, which is pretty easy to find in any standard of US, is that N. Okay, so then you put that, you get D, which, sorry, is in capitals, is the nominal diameter, and then you basically calculate the same thing as before. Okay, the second part of the video is going to be the bolt strength. Okay, and the bolt strength, well, we're going to talk a little bit, or I here have the definition of the stress proof. Why? Because in a bolt strength, when you go to the standard, okay, the bolt strength, you get it from the standard unless you don't have nothing, and then you have to use a material, okay, properties. I would say please try to find and use, when you're going to calculate any kind of bolt calculation, use the standard. That's why it's for. And if something happens and the standard fails, it's not your fault. That is a good thing, okay? Especially when you have to do a lot of calculations. The standard is going to have typically or 2 or 3 of these strengths, okay, which is going to be the tensile strength or ultimate, the yield strength, and then in the bolts they also use the proof strength, okay. And for example, we're going to see a typical, the ISO 898-1 apart from some equations. We're going to have here property class, we're going to have tensile strength here, for example, okay, we're going to have minimum ultimate strength, okay, for the different classes, and then here we have the proof load, okay. So the proof load or proof stress in this case is, as it's going to be defined by checking sorry, here in English, okay, and pretty much is, okay, I like this one more. Proof stress, because the difficulty of getting reliable test results for yield when test full-size fasteners, the proof load test was developed as an alternative, okay? In a proof load test, a headed bolt is placed in the testing machine with a nut on the threaded end and a wedge under the head. The wedge varies from 4 to 10 degrees depending on the size and configuration of fastener and serves to evaluate the ductility of the bolt, okay? In a machine specimen test, you test ductility by measuring elongation and reduction of area, but those are impossible during full-size tests, so head deflection is used in its place, okay? Proof load testing or proof stress, which is the same thing divided by with the area as the difference, is typically performed at 90 to 93% of the expected minimum yield strength, and it's a simple pass-fail test. Okay, it is important to say, based on this ISO 724, that typically, no, I think that one, sorry, it was a mistake. I think it was in the Singlish mechanical engineering book. They say that typically uh, the proof stress is or strength is going to be around 85 to 95% of the yield strength. Okay, this guy was calculated between the 90 and 93 based on Singlish. I think it was between the 85 and the 95. Okay, so to be as conservative as possible, we're going to use that as the number. Okay, so in a lot of standards, for example, sorry, oops. For example, the 898-1 we just saw. Sorry, I'm trying to find the standard. I just don't look. Here it is. So based on that standard, yeah, they give you the proof load, okay, which as he said, proof load and proof stress pretty much is the same thing using the area that we just explained before, okay. But sometimes in some standards, maybe they're not gonna give you, or it could happen, or the manufacturer or something is not gonna give you the proof one. It's gonna give you the yield. In that case, you just multiply by 0.85, which is gonna be the most conservative of all the information or the of the studies that I found. Okay, the most conservative one, just to be sure for safety, is going to be the 85. So use 85% times the yield, and then you just get the proof. Okay, the proof strength, which is also typically defined as SP. Okay, it is then at the end smaller and more accurate than the yield strength based on this definition that I had here. And we will use that one in our analysis, okay? So in the future, when we're gonna start talking about non-preloaded bolts or preloaded bolts, we're gonna pretty much compare all the calculations that I get with the proof stress, okay? Or strength, sorry, of the bolt, okay? And this is pretty much everything for today. In the next video, we're gonna start talking about now specifically the bolts, the two kind of like type of bolt connections that we're gonna find. Okay, it's gonna have a little bit more equations. Okay, this is just a preliminary one. Okay, here with just a little bit of equations here and there and some drawings that I got from the internet. And this is gonna have, as I said, maybe here equations here and there, and then we're gonna have these other ones with also like few equations here and there. Basically, we're gonna start talking about the non-preloaded bolts and preloaded bolts, okay? Then, which is the two types of bolting connections that we're gonna have for a bolt, okay? When it's non-preloaded or when it is preloaded. And then we're gonna talk in the next unit, which is gonna be how we determine the force that is gonna be applied in the bolt, okay? So this is all for today. If any question you had, how to calculate these small equations, as I said, you can ask me, or as I said, check in the ISO, in the standards. This one for equations, and then this one also. And check this book, as I said, for the American Institute of Steel Construction, really good for the US. And then if you want to just check the Singlish or this website, which was the number 4 here, sorry, that was Bolt Council here, that explain a little bit about the proof strength. Okay.